Welcome back. In our previous lecture video, we explored the foundational structure of this market and defined its core product archetypes. Today, we build directly upon that framework to address a fundamental question in additive manufacturing research and industrial design. How do we quantitatively evaluate design quality in the context of domestic, decentralized 3D printing? In conventional mass manufacturing, design quality is traditionally evaluated by production efficiency, assembly line throughput, supply chain costs, and consumer satisfaction. However, when the traditional supply chain collapses and the end user acts simultaneously as the manufacturer and the assembler, these conventional metrics no longer apply. In domestic desktop 3D printing, the core design challenge is not merely producing a printable geometry, but managing product complexity. Here, complexity is not just an arbitrary technical attribute. It serves as a rigorous, analytical design quality metric. It allows designers, researchers, and engineers to evaluate internal design, alternatives, and benchmark products against competing designs in the market. In this video, we present the formal product complexity evaluation framework proposed in the research paper, break down its mathematical parameters, and demonstrate how to measure a product's readiness for use. At the core of this framework lies the product complexity score. The model distinguishes between two primary structural categories: independent products, which are fully 3D printed, and dependent products, which require the integration of non-3D printed complementary components. For a fully three-dimensional printable product, the complexity score is calculated as follows: Cscore equals A, multiplied by open parenthesis, NT minus 1, close parenthesis, plus B, multiplied by NP. For a partially three-dimensional printable product that requires complementary parts, the complexity score is calculated as follows: Cscore equals A, multiplied by open parenthesis, NT minus 1, close parenthesis, plus B multiplied by NP, plus D multiplied by NC. Let's break down these variables. NT represents the total number of parts in the product assembly. NP represents the number of parts requiring post-manufacturing treatment. NC represents the number of non-3D printed complementary components. The core scientific strength of this model lies in the weighting constants, A, B, and D. These constants translate physical handling, production difficulty, and component sourcing into precise numerical values. Consider constant A, the weighted mean constant of part characteristics based on design for assembly methodologies. In conventional manufacturing, assembly is performed by trained factory workers or automated robotics. In domestic production, the skill level, available tools, and the user's age are unpredictable. Therefore, the framework adapts DfA principles to a defined reference user across 5 key criteria: recognition, the visual and geometric contrast of a part compared to others to prevent assembly errors; part size, dimensional suitability for effortless handling relative to a user's hand; handling aids, whether handling requires auxiliary tools, clamps, or fixtures; part orientation, symmetry versus multi-axis asymmetry that could cause incorrect orientation during assembly; ease of handling, part rigidity, and robustness versus fragility, flexibility, or sharp features. Each factor is rated on a 5-point scale from 0.2 to 1. An ideal part contributes a baseline value of 1, whereas a highly problematic part yields a maximum penalty value of 5. Next, constant B represents the difficulty level of required post-manufacturing treatments. Score 1, non-instrumented, manual operations requiring no tools or special skills, such as hand brim removal or easy support detachment. Score 2, basic tool-mediated, standard hand tools addressing minor surface artifacts with low risk of damage. Score 3, skilled manual conditioning, multi-step operations relying on operator skill, such as gap filling, priming, or heat set, threaded inserts. Score 4, infrastructure dependent, treatments requiring dedicated equipment, such as vapor smoothing, UV curing, or thermal reforming. Score 5, integrated multi-stage workflows, complex sequential processes combining multiple high-risk treatments affecting surface quality and dimensions. Finally, for dependent products, the constant D evaluates the accessibility, cost, and assembly skill required for complementary parts, ranging from Level 1 household standard items like bolts or rubber bands to Level 5 specialized mechatronic and power components like controllers and linear actuators. Once the complexity score is calculated, it can be normalized into a single bounded index from 0 to 1. Readiness for use, RFU equals 1 over open parenthesis, 1 plus Cscore close parenthesis. When a product consists of a single part requiring no post-manufacturing treatments, Cscore equals 0, resulting in an RFU of 1, indicating immediate operational readiness. As assembly parts, post-processing steps, and external hardware dependencies increase, RFU approaches 0. How does this framework serve as a design quality metric when evaluating design alternatives for the exact same product? Let's analyze 2 design iterations for a functional desk lamp, focusing on the trade-off between geometric consolidation and post-processing. Both designs integrate the exact same standard electrical components, a lamp socket and a power cord, NC equals 2. Sourcing and wiring these standard parts requires basic technical handling, establishing a complementary component score of D equals 3. In Design Alternative A, the designer divides the lamp into 3 primary 3D printed parts, a base, a central stem, and a single-piece shade, NT equals 3. Because the large unified shade is unwieldy and geometrically unbalanced during handling, the average DfA constant increases to A equals 1.6. Furthermore, while the base and stem print cleanly, the complex curve of the unified shade requires extensive internal supports. Detaching and cleaning these supports from that single shade requires skilled manual tool work. MNP equals 1, B equals 3. Calculating the Cscore for alternative A. Cscore equals 1.6 multiplied by open parenthesis, 3 minus 1 close parenthesis, plus 3 multiplied by 1 plus 3 multiplied by 2. This equals 3.2 plus 3 plus 6, which equals 12.2. This results in a readiness for use of 1 divided by 1 plus 12.2, which equals 0.076. Now consider design alternative B, where the designer splits the large shade into 2 modular, self-supporting halves that easily snap together, bringing the total assembly to 4 3D printed parts, E or NT equals 4. The smaller symmetrical shade segments significantly improve handling characteristics, lowering the average DfA constant to its baseline minimum of A equals 1.0. Crucially, because both shade halves print cleanly without supports, 0 post-processing steps are needed. NP equals 0. Calculating the Cscore for alternative B. Cscore equals 1.0 multiplied by open parenthesis, 4 minus 1 close parenthesis, plus B multiplied by 0, plus 3 multiplied by 2. This equals 3.0 plus 0 plus 6, which equals 9. This pushes the readiness for use up to 1 divided by 1 plus 9, which equals 0.100. Comparing the 2 outcomes shows that by splitting the shade into 2 parts to eliminate support post-processing and improve handling, the Cscore drops from 12.2 down to 9, causing the RFU to jump from 0.076 to 0.100, a 31% increase in operational readiness. This comparative analysis reveals a fundamental theoretical insight. The complexity score and the readiness for use index are not absolute pass or fail scores for a design. Rather, their true analytical value emerges when evaluating and comparing distinct design alternatives. Through this mathematical lens, design sources can systematically step into the shoes of the domestic end user. The framework translates the user's physical assembly burden, post-processing friction, and hardware sourcing effort into concrete quantitative data, allowing designers to optimize CAD decisions before a single file is ever published. In conclusion, this product complexity evaluation framework provides a rigorous methodology to bridge the gap between digital design intent and successful domestic fabrication. If you are a student considering master's or doctoral research in design for additive manufacturing, distributed production, or product complexity, I invite you to reach out to explore potential co-advising and research opportunities. Likewise, this invitation holds for industry leaders, researchers, and professional practitioners pushing the boundaries of domestic additive manufacturing. Thank you for watching. I invite you to read the papers listed below for a deeper dive into this research. See you in our next lecture.